Let's talk about the characteristic equation now of an AR2. And in addition, we'll talk about the roots of this characteristic equation and how they relate to stationarity. We'll also extend that here at the end and talk about the behaviors associated with that particular model and a little bit more at the end. So let's go ahead and change this into backshift notation so we can get the characteristic polynomial and thus the characteristic equation. So again, we can learn about the stationarity or non-stationarity of this model. So to get this into backshift notation, we'll first say, okay, this is the same as 1 minus 0.1b minus 0.72b squared xt equals at. Great. And we note there that this is xt times 1 is xt times negative 0.1b is negative 0.1 xt minus 1, b to the first, xt is xt minus 1, minus 0.72b squared times xt is minus 0.72 x to the t sub t minus 2 equals at. So great, we've got it into backshift notation. Why do we do that? So we could get all the information about this model in between the parentheses here. We're going to draw our 3 lines here to denote that I'm not rewriting this equation. I'm done rewriting the equation. I've got all the information over here, and that's all I need to make the characteristic polynomial, which we'll call 1 minus 0.1z minus 0.72z squared equals, and that's the characteristic polynomial. If we set it equal to 0, then we have the characteristic equation. Great, notice the b's have become z's because b is an operator and we're writing it as z to designate that as a variable. And the theorem states that all the information is in here, and if we write that lagged information as a polynomial, we can learn a lot about the stationarity and some other stuff. So other stuff that we'll talk about here in a moment. So this unique property of polynomials are that a degree in polynomial, any polynomial, can be written uniquely as a product of degree 1 and degree 2 polynomials. It could just be broken down into degree 1 and degree 2 polynomials. Uniquely, meaning we don't get to choose if it's degree 1s or degree 2s. We factor it and we see what we end up with. This is a degree 2, so it can either be irreducible, and that's it, or it could possibly be factored into degree 1 polynomials. So let's see, I happen to make this polynomial, I started with this polynomial, so I know it can be broken down. It can be factored into degree 1s. And we will have some software that will help us factor these for us. But again, this one can be easily broken down. So let's see how it works out. I just need 2 numbers that multiply together to give me negative 0.72, but that add together to give me negative 0.1. And those are 1 minus 0.9z and 1 plus 0.8z equals 0. If you FOIL that out, you get negative 0.9 times 0.8 gives you negative 0.72, and negative 0.9 plus 0.8 gives us negative 0.1. So I've broken down, this one happened to be able to be factored into 2 degree 1 polynomials, and now I've got my characteristic equation, but it's factored, and I can look at the 2 roots. So here I'll have 2 unique real roots. So root 1, I'll take the first factor here and set it equal to 0. 0.9z equals 0. Because if 2 things multiplied together equals 0, then either this one can be 0 or that one can be 0, or they could both be 0 to give you that product. So what is the z that makes this one 0? Well, that would simply be negative 0.9z equals negative 1. Z equals negative 1 over negative 0.9, which equals 1.11 forever. And we see that that is bigger than 1 in absolute value. It is outside what we'll call the unit circle. We'll define that more here shortly. But this one is a stationary factor. This factor is associated with stationary behavior. So let's look at root 2. So root 2 here would be this, from this factor, 1 plus 0.8z equals 0, and we've got 0.8z equals negative 1, z equals negative 1 over 0.8, which equals now negative 1.25, which negative 1.25 is again bigger than 1 in absolute value. It is outside the unit circle, and thus this factor is associated with stationary behavior. This factor has roots outside the unit circle associated with stationary behavior. So this whole model is a process, represents a process, a stationary process. So that's really the big picture. We have an AR2. We came up with a characteristic polynomial, put it in backshift notation, came up with the characteristic polynomial, found the roots of that, set it equal to 0 to get the characteristic equation, and then factored it to get the roots of the characteristic equation, found that they were both outside the unit circle, bigger than 1 in absolute value, so this is a stationary model. Now, one thing a seed I'd like to plant going forward is that note that this is associated, if we were to write this back in backshift notation, this degree 1 polynomial here is associated with an AR1, as is this one is. And this one would be associated with wandering, because that's a positive phi1, right? 1 minus 0.9, if that was a B, this would be associated with wandering behavior. This one's associated with oscillating behavior. But what we notice is that things don't just oscillate or not oscillate, or they don't wander or not wander. They're expressed at different magnitudes. So one way we can measure that magnitude of the expression of this wandering or oscillating behavior is through what's called the absolute reciprocal. Before we approach that concept of the absolute reciprocal, again, we're just planting that seed. We're going to talk about that a lot more in the future, but this is the ideal place to introduce it. We note that the closer this root is to 1, closer it is to what we'll call the unit circle, the more that behavior will be expressed. So this one, 1.11, is closer to 1 than negative 1.25. So the wandering in this case will be expressed more than the oscillating behavior. But another way, or a little more standard way that we can look at it, one way we'll look at it quite a bit, is through a scaled version of this called the absolute reciprocal. So the absolute reciprocal must be between 0 and 1. And the closer it is to 1, the more that behavior will be. So the absolute, I'll just say reciprocal. So if I do 1 over root 1, the reciprocal of root 1 is 1 over 1.11, just to see what that is. 1 over 1.11 is 0.9. It's pretty easy with this when it factors into two AR1s, because the reciprocal of the root is just the coefficient that the root came from. But that's 0.9, and then 1 over root 2 here is 1 over, notice it's the absolute reciprocal, so I'm just going to put positive 1.25 there, which equals 0.8. So this one, this wandering behavior factor, the factor associated with wandering behavior, has an absolute reciprocal of 0.9, which is a little bit closer to 1 than this factor associated with oscillating behavior, which has an absolute reciprocal of 0.8. So this one, again, will wander more than it oscillates. But again, with a 0.9 and a 0.8, we'll probably be able to see both of those behaviors, and we will see those in a future video. So great job. Recapping, we had a model, we put it into backshift notation, we had the characteristic polynomial that we then set equal to 0 to get the characteristic equation, which we could then factor uniquely into degree 1 and degree 2 polynomials. This one happened to factor into 2 degree 1s associated with 2 AR1s, one wandering, one oscillating. We found that the roots were both outside the unit circle. Thus, this whole model is associated with stationary behavior, where it's going to wander a little more than it's going to oscillate, because these absolute reciprocals, this one's closer to 1 at 0.9, this one's a little farther from 1 at 0.8. So great job. I'll see you in the next one.